Welcome back, Physical Science 20. This is the PW2.5. The first part, we'll look at curved mirror reflection. So in PW2.4, we looked at flat mirror reflection. Now we'll look at what curved mirrors seem to do. So there's two parts. Part one will be a drawing section in which we figure out things, and part two will be a more mathematical method of figuring out all the items we need to figure out. So investigate image formation in convex and concave mirrors by constructing ray diagrams. So that's what I mentioned. We'll be doing that. You'll need a ruler for this section. Identify the properties including type of image, whether it's real or virtual. We talked a little bit about virtual images with plane mirrors. Attitude or orientation, whether it's upright or inverted. Magnification, whether the image is smaller, larger, or same size as the object. And position relative to the mirror surface or vertex of images formed in concave and convex mirrors. And distinguish between the meaning of concave mirror, convex mirror, principal axis, focal length, focal point, real image, magnification, and spherical aberration. So if you look at a surface of a shiny spoon, that actually is a concave or convex mirror. You'll notice that your reflection is different from what you see in a plane mirror. The spoon acts as a curved mirror, with one side curved inward, the other side curved outward. The properties of curved mirrors and images that they form depend upon the shape of the mirror and also where the object is. So concave mirrors, we'll start with that. The inside of surface of a shiny spoon, the side that holds food, acts as a concave mirror. A concave mirror has a reflective surface, the edges of which curve towards the observer. So concave curves towards you, towards the observer, towards the object. Properties of concave mirror depend on how much it is curved. The figure on the right, or right down here, shows how a spherical concave mirror works. In a spherical concave mirror, the mirror is shaped as if it were a section of a hollow sphere with an inner reflective surface. The mirror has the same geometric center, C, and radius of curvature as a sphere of radius r. So if you look at this, here's the mirror here, a section of it. So you can imagine if I was to extend this into a sphere, C represents where the center of that sphere would be. And the radius from the center of the sphere to where the mirror is the radius of curvature. So we have to envision that. A curved mirror, think of it as a big sphere where C is the center and R is the radius. The line that includes the line segment CM, so going from the center to where it hits the mirror, is called the principal axis, which is a straight line perpendicular to the surface of the mirror. So if we were to look over here, this of course would be a perpendicular 90-degree angle. And quite often we envision the mirror as a straight line here, you'll see, as when we draw diagrams. Point M is the center of the mirror where the principal axis intersects the mirror. If we move on to the next page, when you point the principal axis of a concave mirror towards the sun, all of the rays are reflected through a single point. You can locate this point by moving a sheet of paper toward and away from the mirror until the smallest and sharpest spot of sunlight is focused on the paper. So if we take a look over here, the sun rays come in parallel to the mirror. So if you hold this mirror towards the sun, and they will be reflected. And you can actually catch that reflection on a piece of paper. That point is called the focal point of the mirror. So it can be determined by looking at what a distant illuminated object, how it would appear on a piece of paper. That tells you the focal point of the mirror, where all the rays are directed to. So the spot is called the focal point of the mirror, the point where incident light rays that are parallel to the principal axis converge after reflecting from the mirror. The sun is a source of parallel light rays because it's very far away. All of light that comes directly from the sun must follow almost a parallel path to the earth, just as all arrows shot by an archer must follow almost parallel paths to hit within the circle of a bullseye. When a ray strikes a mirror, it is reflected according to the law of reflection, so angle I equals angle R. The figure on the previous page shows that a ray parallel to the principal axis is reflected and crosses the principal axis at point P, the focal point. So if you take a look back at this diagram, so a parallel ray comes in. When it hits the mirror, especially if it's a curved mirror, angle I equals angle R, it reflects out and goes through that focal point. Okay? Let's see where we're at here. So it shows that F is at that, oh, here's another thing to note. F, if you noticed, is at the halfway point between the mirror and the center of curvature. So if you take a look here, it's exactly halfway between. So you have the center of the mirror to the mirror, the focal point is halfway. So if we have this being the focal length, if you take 2 times the focal length, you'll get R. It's exactly halfway, or if we take twice this distance, we get the entire radius of curvature. So the focal length F is the position of the focal point with respect to the mirror along the principal axis. And as you can see here, it's half of the radius of curvature. Okay, so those are some things that are true with concave mirrors. The focal length, focal point, center of curvature, radius of curvature, and of course a line joining the center of curvature to the mirror is called the principal axis. All right, so now we'll look at how can we find the image graphically by drawing diagrams. You've already drawn rays to follow the path of light that reflects off plane mirrors. This method is even more useful when applied to curved mirrors. Not only can the location of the image vary, but so can the orientation and size. You can use a ray diagram to determine properties of an image formed by a curved mirror. The figures below show how the formation of a real image occurs by a curved mirror formed from the converging rays of light. Okay, so a real image will be picked up on a screen. So you can actually see it on a piece of paper, unlike a plane mirror image, which appears behind the mirror. So if you take a look, here's all the scenarios we're going to do. We're going to look at what happens if we place the object in between C and F, etc., and we'll be able to see that. So you can see there's some principal rays here that we'll be looking at in parallel out through F, out parallel, which is just vice versa. And you can see the image would be picked up over here. And if we had a piece of paper, we would in fact be able to see it. So we have that. So all these rays come back to our eye. But if we put a piece of paper there, we would actually be able to see that image on a screen or on a piece of paper. So as you can see, the image is inverted, and it's larger in this case. The rays actually converge at a point where the image is located. The point of intersection I of the 2 reflected rays determine the position of the image. So you can see, if I look at just taking a piece of that object, just the top part, the bottom part is on the principal axis, so the bottom part of the image is on the principal axis, but the top you can see is going to be upside down, so it's actually inverted. You can see the image floating in space if you place your eye so that the rays that form the image fall on your eye, as in figure A. As figure B shows, however, your eye must be orientated so as to see the rays coming from the image location. You cannot look the image from behind. If you were to place a movie screen at this point, the image would appear on the screen as shown in figure C. You cannot do this with virtual images such as plane mirror images. To more easily understand how ray tracing works with curved mirrors, you can use a simple one-dimensional object such as an arrow. Quite often we'll just simply use an arrow as opposed to a 3-dimensional object and pick a point on that arrow. Usually the bottom point will be on the principal axis, so the image is on the principal axis. The top part, if we can map out what happens to that top part, we'll be able to figure out if the image is bigger than the object, whether it's inverted or upright, etc. A spherical concave mirror produces an inverted real image if the object's position, DO, or object distance, is greater than twice the focal length. The object is then beyond the center of curvature. If the object is placed between the center of curvature and the focal point, as shown in the figure that we did on the left here. So here you have the object. and then it was placed upside down here, and you can see the image is opposite to it, so inverted. However, the size of the image is now greater than the size of the object. And you could actually do this with the spoon by looking into it and altering the distance between you and the spoon. How can the inverted real image created by a concave mirror be turned right side up? In 1663, Scottish astronomer James Gregory developed the Gregorian telescope, shown in the figure below, to resolve the problem. So there's a couple of reflections that happen here so that the image appears upright, as opposed to just looking through one mirror. It is composed of a large concave mirror and a small concave mirror arranged such that the small mirror is outside the focal point of the large mirror. Parallel rays from the distant object strike the large mirror and reflect toward the smaller mirror. The rays then reflect off the smaller mirror and form a real image that is orientated exactly how we would see it. Right, I think what we'll do is we'll stop right there. Then we'll look at kind of the rules for ray tracing, and then we'll run through all the possible scenarios that we could end up with.